So today we're going to start Chapter 9, and we're looking first and foremost at Section 9.1, where we're going to talk a little bit about probability and determining probabilities. A lot of vocab, a lot of definitions and theorems and things like that here at the beginning, so just bear with me until we can get to some more interesting stuff further on in this section. So to start with, an experiment. So certainly like a scientific experiment would count, but what we're doing is a far more broad definition. An experiment is simply any activity whose results can be observed and recorded. Experiments don't even have to be numerical in content. So when you guys go doing your observations in the schools with your with your teacher ed stuff, those are experiments because you're observing what's going on. So when we're looking at this one, we are going to be doing things with more mathematical values involved. So, flipping a coin 100 times would be an experiment, right? Recording how many times someone says or like would be an experiment, okay? So you can count those things. An outcome is each possible result of an experiment. So if we were flipping that coin, the two outcomes are either heads or tails. There's only two. If you're rolling a dice, you have 6 different outcomes, a standard die, and so forth. Sample space is the set of all possible outcomes. So let me do my coin example, right? The two outcomes are heads and tails. So the sample space would start with, I'll write this one down just so that it's recorded, head and tails, would be a curly brace. And then you'd write all the possible outcomes inside of the curly brace. That's what a sample space is. It's just a listing of all the outcomes. And then an event is any subset of the sample space. So my example that I've used doesn't lend itself very well for me to do an event. But if you can imagine me doing a die example instead, the sample space would be the curly brace, the numbers from 1 to 6, and then into the curly brace, right? And then an event might be rolling an odd, or an event might be rolling a prime, okay, something like that. So an event is it can be rolling a 1, but it can also be sort of encompassing multiple outcomes at once. The law of large numbers, Bernoulli's theorem. This is the idea that if an experiment is repeated a large number of times, the probability approaches a fixed number. Right, if I flipped the coin a large number of times, I don't mean like 50, I mean like maybe 600 or 12,000 or a really large number of times, you would expect about 50% of the outcomes to be heads and 50% to be tails, right? Over time, that's what that would look like. So the probability is actually calculated as the number of items in your event or whatever you're wanting to have happen, A, divided the number of items in the sample space. So along with this idea, if we're thinking about my heads and tails example on my previous slide, if I wanted the probability of getting heads, oops, I was supposed to put an H there. This would be the number of heads divided by the total number in the sample space. Well, if you look at the sample space that we wrote down, there was 1 head, and there were 2 items in the sample space. Okay, so when you put the N in front of the notation, it means number. When you put the P in front of the notation, it means probability. Okay, it's not multiplication with those parentheses going on or anything like that. It's used notationally to mean the number of a specific thing happening or the probability of a specific thing happening. All right, mutually exclusive events. Events A and B are mutually exclusive when they have no elements in common. That is, A intersect B equals, and this right here is the empty set. In number theory, if you've had that class already, we encounter that symbol. We talk about it being called the empty set. Every now and then I have students who want to do a 0 as this symbol, a 0 with a slash through it. And I have to remind them, if they haven't, especially if they haven't encountered it already, that that has another meaning. We can't use that symbol to mean the number 0. It means empty set. So empty set just means it's a set of collection of things that have nothing in it. For instance, if I were to say the infants in my home, that's an empty set right now. I don't have any infants in my home, okay? So mutually exclusive events are things that cannot happen at the same time. So if you're thinking about like my rolling my die example, I cannot both roll an even and an odd. Those events are mutually exclusive. If I did, just to make sure I'm not asking the same question later now. If I talked about rolling an even and rolling a prime, those aren't mutually exclusive because the number 2 is both even and prime. All right? So just because things are different doesn't mean that they might not have something in common. And that's what we're wanting to be careful about when we talk about the phrase mutually exclusive. Mutually exclusive often gets confused with another phrase that we're going to encounter a little bit later, and I'll mention it when we get there, and it's called independent. They're not the same thing, but they have some sort of like emotional attachment that they feel similar. You know what I mean? They feel like they're similar, but they're not quite the same thing. So mutually exclusive means they don't have anything in common. Theorem 9.2 talks about probabilities and the value that they are allowed or are able to hold. So a probability, if A is any event and S is the sample space, then the probability of our event is between 0 and 1. So when we came in and Jenna was asking me about the probability of us having homework this evening, I inadvertently said, what did I say first? I said 0, and then I said something else. I said maybe 10. I think that's what I said after that. I was like, maybe 10. And then I stopped myself because the way I said it was incorrect, right? It wasn't 10. I meant 10% or 0.10 or 0.10. So when we're talking about probabilities, we're looking at numbers that would be between 0 and 1, which would correspond to percentages between 0 and 100%, okay? So that's what we're looking at for probabilities. So there's not a probability of something happening that's 150%, right? It's not a probability. That doesn't make any sense. The probability of an event, Theorem 9.3, the probability of an event is equal to the sum of the probabilities of the disjoint outcomes making up the event. So that's a really awkward way of saying something that you likely would have naturally come to the conclusion of anyway. So if you were to consider rolling a 6-sided die, let's talk about the probability of rolling even. So this is the probability of rolling a 2, a 4, or a 6, which is the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. But that only works because 2, 4, and 6 are they're individually different, right? They're disjoint outcomes. They cannot both happen at the same time. They're also mutually exclusive, like we talked about before. Okay, so when we have things that are mutually exclusive or disjoint, we can actually separate them and talk about the individual probabilities and add them all together. And sure enough, if you think about counting it this way, this would be 3 outcomes out of 6. This is 1 outcome out of 6 plus 1 outcome out of 6 plus 1 outcome out of 6, and of course those add up to the same quantity. Okay, so if we do have mutually exclusive events then if you want the probability of either or, right, either one or the other happening, A or B, this is actually the same as finding the probability of A plus the probability of B. And what I just wrote down on the previous example is exactly an example of that happening. 2, 4, and 6 are mutually exclusive events. So I can separate out the possibility of any of those 3 happening by finding the probability of each one individually happening and adding them together. Now, if you have something that is not disjoint, that's a problem, and it doesn't work out that way, right? I cannot find the probability of rolling an even or a prime by simply finding the probability of rolling an even and adding it to the probability of rolling a prime because they overlap. They're not disjoint. Theorem 9.5 may include notation that you're not familiar with, again, depending on if you've had number theory. You see notation right here that has a a bar, for lack of better terms, I guess, on top of the A. That bar on top of the A is what we're using to represent a complement. So if A is an event, then what we mean by the complement is things that are not A. So if I want the probability of rolling an even, well, then the complement of that would be not even or odd. If I want the probability of rolling a 2, the probability would be the probability of not a 2, which would be 1, 3, 4, 5, and 6, right? So complement means everything not described, the opposite of the things that you are describing. And so the reality is, if you take the probability of an event and the probability of its complement and you add them together, you get 100%, right? What's the probability that it will rain today or that it will not rain today? 100%. It's one or the other, right? Definitely going to happen. So we're actually add those two complements together and we get 1. The other two equations below that are just rewriting the first equation differently. So you notice that if you subtract this one to the other side, you get this equation. And if you subtract this one to the other side, you get this equation. So they're just rewritten forms of the same equation, 3 different forms. Okay, one more set of precursor information, then we'll do some examples. These are a summary of probability properties. The first one talks about the probability of the empty set. So this is also known as an impossible event. The probability of the empty set is 0. Right? So the probability that you will go to my home and find an infant living there right now is 0. It's an impossible event because it doesn't exist at the moment. The second one, P of S equals 1. That's actually a certain event. It's guaranteed to happen. And again, if you think about it in terms of percentages, you would be inclined to be like, well, yeah, of course. Because a probability equal 1 is 100%. It's guaranteed going to happen. The other one says the probability of the empty set being 0%. Well, it's guaranteed not going to happen. Okay? And what that means then, the third bullet point is actually something we've already written down today, is that every probability is between 0 and 1. It's between 0% and 100% chance that something will happen. The fourth bullet point we've also encountered today. It says that if we have mutually exclusive events, A and B, that's what A and B equal the empty set. Let me also make one more mention. This notation is intersection. It means what they have in common. This notation is union. It means all of everything they have combined together and dumped into a bucket or whatever, thrown all together in the mix. So if they have nothing in common, that's what the first half of this if-then statement says. If they have nothing in common, then the probability of taking everything that they have and joining it together is simply the probability of each of the events independently added together. But like we mentioned before, sometimes we don't have independent events. And when we don't have independent events, we have this fifth bullet point. So it looks much like the first one we had, or the equation that we had in the fourth bullet point. The part that I've underlined matches, in fact. The probability of A union B is the probability of A plus the probability of B. But we have to remove the double counting. So in my example with my even numbers and my prime numbers, if I count the number of even numbers and find the probability is 1/2, and I count the number of prime numbers and find that the probability is 1/2, but then I recognize that they had something in common, namely the number 2, I would have to remove the probability of rolling a 2 because I counted it twice. I counted it when I counted evens, and I counted it when I counted primes. So I would have to remove that double counting, and that's what you see happening here at the end, is that you're removing the probability of whatever it was that they had in common. And again, you're only removing it once because you counted it twice. You don't want to remove it completely, all right? But you need to remove it once because it was counted twice. And then the sixth bullet point, again, we've already seen as well, It's the probability of the complement. It's one of the versions anyway. The probability of the complement is 1 minus the probability of A. So if I were to go look at my phone right now and I wanted to know what's the probability that it's going to rain today, and I found out the probability that it was going to be raining, well, of course, the phone will give me a percentage, 40%, right? Then that would mean, likewise, the probability that it's not going to rain is 60%. And that's because 40% 0.4, 60% 0.6, you add them together, you get 100% or the number 1. So I like having this summary table because everything that we've listed, almost everything, is actually on the previous page, but this is all in one concise place for you to go back if you needed to reference any of it. Okay, so we're going to look at some examples. Some of our examples are going to require a bit of knowledge of different kinds of games. And the first one is specifically not a game, but a card deck. So you may or may not be familiar with card deck, depends on what kind of games you've played in your past. So I want to run through a few things to make sure you have enough knowledge to be able to answer the questions in case you haven't used cards very frequently. So in a card deck, so jot these things down, especially some of the numbers that you may not be aware of anyway. There are 52 cards. Half red, half black. So there's 26 red, 26 black. Let's see. We have 4 suits. All right. So there are 13 diamonds and 13 hearts. Those are all of our red cards. And then there's 13 spades and 13 clubs. And those are all of our black cards. We have several different, what we would call face values of cards. Some of them have numbers, and some of them have royalty. So they start with the number 2. So there's not an actual number 1. They go from 2 to 10. So we have the digits in each of those suits. There's a 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so that's 9 of the cards and of the 13 in each of your suits. You also have royalties. So the royalty are the jack, the queen, and the king. And then that's 12 of my 13 cards. The last card's an ace. And there's an ace then in every one. Okay, pretty good so far. All right. I'm not asking you to sort of, there's no questions that will ask you like, which is a better value or a lesser value for a game. So then none of that's relevant. We're simply counting things in this question and in any future questions that relate to cards. So consider drawing a single card from a standard deck of cards, right? So this is like, your nephew coming up and spreading out the cards, and he's going to do card trick, and he says, pick one, all right? They're all just sitting there, and you just choose a card out. We're going to decide if the following events are equally likely or not equally likely. And we're going to go one step further, and we're going to actually find the probability of each event to make the comparison. But the comparison is simply the answer that we need to be writing down specifically. It needs to say either that they're equally likely or not equally likely. So we've got a face card and not a face card. So I have ace is not face cards. Ace is not a number. Okay, ace is just an ace. So the royalty cards are your face cards. And if you were to see them on a deck, they'd actually look like they have faces on them. Most decks anyway. You actually see a king or a queen or a jack. All right? And we're not using jokers in our deck. That's not part of my 52, by the way. So if you picked out a card and it had a face on it, how many different faces could you have picked? Well, there's 3 faces that are hearts. There's 3 faces that are diamonds, and there's 3 face cards that are clubs, and there's 3 face cards that are spades. Is everybody with me? How many is that? We had 12. So we're just going to write these out as non-reduced fractions because the comparison is a little bit easier than trying to reduce the fractions. This is 12 out of the 52 cards. I think let me change my color so at least it stands out from my questions. Let's try that. All right, that's a little bit better. There's 12 out of 52. How many cards are not face cards? Well, everything else, right? How many everything else's are there? 40. So how did you get it so quickly? Because I know you didn't count. Yeah, you just subtracted. So there's 52 cards. If I take out 12, then there's 40 left. So the probability of pulling out a face card is 12 out of 52. The probability of pulling out not a face card is 40 out of 52. Are these equally or not equally likely events? They're not equally likely. So that's the answer to the question. And the numbers that we wrote down are our justification as to how we made that decision. So that's the show the work part. The answer is not equally likely. Writing down the numbers shows the work. Now, if we were really asked to find the probabilities of these, we'd reduce those fractions. But there's no need to reduce the fractions because that's not what I'm being asked. Does that make sense? So definitely if the question asks you for the probabilities, we'll put them in reduced form. But if we're just using the probabilities to make a decision about something, we don't need to. How about the next ones? Clubs, diamonds, hearts, and spades. So how many clubs are there? 13 out of the 52. How many diamonds are there? 13 out of the 52. How many hearts? 13 out of 52. And how many spades? 13 out of 52. Are these equally likely? Yes, these are. All of them match. These are equally likely. All right. How many black cards are there? 26 out of 52. And how many red cards are there? 26 out of 52. Are these equally likely? Yes, they are. All right. We've got lots of things listed here. How many kings are there? 4 out of 52. How many queens? 4 out of 52. Jacks? 4 out of 52. Aces? 4 out of 52. And just so that everybody's aware, remember they're getting 4 because there's 4 suits. There's one of them in every suit. How many evens are there? Are there? Close. Careful now. 5 out of... There's 20. Okay, good. All right, so you're processing through. You're thinking the right thing. You just need to continue it on. Okay, so there are 5 even numbers in each suit, right? There's a 2, 4, 6, 8, and 10. There's 5 even numbers, but I have 5 even spades, and I have 5 even clubs, and I have 5 even diamonds, and I have 5 even hearts. Make sense? So that is 20. So up to this point, it would have been equally likely, right? But now I've spoiled it. There are 20 out of 52 even cards. How about odd cards? What is it? I don't think it's 12. I think it's 16. Let's count. So there's no 1, right? But there's a 3, 5, 7, and 9. So there's 4 in each suit times the 4 suits, so that's 16. There's 16 out of 52. And are these equally likely? No, they are not equally likely. Now, the first 4 of them are equally likely. So if that had been where my problem stopped, the answer would be yes, but once we included the evens and the odds, it's no longer true. Okay, any questions on that? So what we did was just counting of cards, but not in the illegal counting of cards kind of sense that everybody doesn't like, okay? Yeah. All right, let's do another example that doesn't include a game. A civ class is composed of 21 men and 34 women. There are 22 education majors, 13 religion majors, 12 science majors, 5 English majors, 3 math majors. And for the purposes of our discussion, we're assuming that nobody's double majoring in any of those things, okay? I know double majors exist, but for the purpose of what we're talking about here, that's not our discussion. So we're going to answer some questions. Assuming no one has a double major, if a single student is chosen at random, what is the probability that the student is? And it gives a category. So the first thing we might want to do is what? count how many people there are total. So somebody grab a calculator or whatever and count for me, how many total people do we have? 55. Yeah, you're right. So I have 55 people total. It's a little bigger than our civ classes actually are. Unless they're this semester and they've joined them all together, and then they're much bigger than that, right? Yeah. All right, females then. What's the probability that you select a person at random, right? Imagine putting everybody's name in a bucket. You pick the name out, and the person's name you picked out's a woman, okay? That's the goal here. So how many females are there? 34 out of our total 55 students. Does that reduce? No, it doesn't. If it did, we would reduce it, but it's done at this point. So the probability that we've selected a female's name is 34 out of 55. How about a science major? Yeah, 12 out of 55. Will it reduce? What will it divide by? Nope, I don't think it'll divide by anything. 12 is divisible by 2 and 3, at least in terms of prime numbers, and 55 does not divide by 2. Do you guys know the trick for divisibility by 3? Okay, good. Yeah, and so we talk about that one in number theory. If you add the digits together, in this case 55 would be 5 plus 5. 5 plus 5 is 10. Does 10 divide by 3? Then neither will 55. That's the trick for 3. It works for 9s too, by the way. All right, so we're reduced at that point. Now this one says an English major or a religion major. Well, since there are no double majors, what can I do to find the number of people in that category? Yeah, I can just add the religion major and the English major numbers together. What is that? 18 out of 55. It doesn't reduce either. We'll just jump to the end of that one. No more reducing on that one. All right, so Part D says neither a math major nor a science major. So what am I really going to be doing, or am I asked to do on that problem? Add, what was that, Katie?
Add all the other majors.
You could add all the other majors together, right? That's one way to do it. What else could you do? You could. You could add the math and the science together and subtract them away from the 55. So either of those options works pretty much equally well in this particular problem. One's not more work than the other or anything like that. So if we add them all together that are not science and not math, or if we do this subtraction that we described, what do you get? It is 40. 40 out of 55. Now, does that one reduce? Yes. We can divide top and bottom by 5, right? And what will that give me? 8 over 11. All right. The next page is several questions that are more like type C kind of questions, right? It's not called communications. What does your book call it? Connections. Thank you. The connections question. So let's take a look at the first one. Example 3. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What is your reply? Say it louder for me, Emma. 5 is not a big number. That's valuable, right? So the law of large numbers doesn't apply. Now, that doesn't mean the student's right or wrong necessarily, but at least that part of it makes no sense to talk about. Does that make sense to you guys? Law of large numbers doesn't make any sense to talk about when we talked about like flipping a coin or whatever it was 5 times, and then we're doing it the 6th time. So that's one valuable piece of information. So one of the things to making a decision about whether or not that's sufficient and that's enough to actually say we're done with the problem is to say, if I fixed that problem, if I had a number big enough, would his argument still hold? Or is there an additional flaw that I need to be aware of? And if so, what is it? So let's say that he tossed the coin 5,000 times and it came up heads. Assuming it's a fair coin, which would be awfully strange, right, that this happened if it were, but awfully strange. Would it be more likely that on the 501 tossed time that it would now come up tails instead of heads? No, but why? Yeah, and let me tag on to what you said a little bit further, Destiny. It is a 50-50 chance. But a reason that it works that way is because each flip, in this case the flip of the coin, is an independent event. I haven't exactly talked about that yet in those words, but each time we flip the coin is no bearing on what happened before or what will happen later, right? They're separate individual experiments each time, basically, right? It's an experiment. I flip the coin, that's my experiment. I can flip the coin again, and it has nothing to do with what happened previously or what will happen in the future. So that's my other issue. So even if the large number issue were not going to be an issue, that's an additional problem here. So each flip is independent of any prior outcome. $50-50 every time, no matter what happened before. Any questions on that one? So be careful when you're working with problems to not just, hone in on one piece of it. See if there's anything else that's wrong, because sometimes there's more than one thing wrong with our reasoning. In fact, every now and then there's multiple things wrong that each actually end you at the right solution, but not from the right point of logic. So be careful with that. Let's take a look at a dartboard. No, a spinner. Sorry, this one's a spinner. The following spinner is spun 100 times. Joe claims that the number will occur most often, the number 4 will occur most often because it has the greatest area of space on the spinner. What would you tell Joe about his conjecture, and what is the probability that 4 will occur on any spin? 2 questions. Let's start with the first one. What about Joe's conjecture, his theory? Okay, so the probability, I'll say it that way. The probability of landing, I'm not sure landing is exactly the right word, but pretend for a moment. Landing on any number depends on the angle. Faith, was that you talking to me? Okay, tell me what else you want me to say. It depends on the angle.
Not the amount of space.
Okay.
Area.
So not the amount of area. So why is that true in this context? Why does it depend on the angle and not on the area? Okay, so each angle has 90 degrees, but why is it the angle that matters instead of the area mattering? Grace? Yes, you're right. So the spinner goes through angles. It doesn't go through numbered regions, really, right? It goes through the angle measure associated with the numbered region, not the area associated with the numbered region. Right. So not the area, amount of area. Because the spinner spins through areas. I'm sorry, through angles, not through areas. So that was sort of question number 1. Question number 2 said, what is the probability of spinning a 4? So, Jenna, you were telling me about the 90-degree markers. Any idea what the probability would be then based on that idea?
1/4.
Yeah, it's going to be 1/4. And it's not because there's 4 numbers, actually, right? It's because they're equally likely and there's 4 regions. So what we really have, going back to your idea of 90, is that there's 90 degrees out of the 360 degrees that our spinner is spinning through. So that's really where the 1/4 is actually coming from. So let's change the context just a tad. What if it's a dartboard instead of a spinner? Would Joe's response be correct or incorrect at that point? Correct. Why? Yeah, so it's actually interesting, not only that, but the dart might not even land on that silly board, right? This is the reason we just told our teens at our church that they cannot have a dartboard in the teen room. We want to protect the walls right now. It's brand new walls, no dartboards. So yeah, the dartboard goes towards areas, not towards the angle measures. The angle measures don't have any bearing on that at all. So he's correct if it's a dartboard. Because the more area you have in a region, the more likely the dart will land there. However, sort of the second question of what's the probability of the dart landing in the section 4, we can't determine that, right? There's no way to determine the probability of that. So the probability of 4 is we'll say not computable. I have no ability to do that. Now, if I were talking about a specific person and their likelihood of hitting that, I might be able to create that based upon their success at doing so. So if, again, think about like the law of large numbers. If you watched them throw the darts at this board, and you watched them do it, 500 times, you could count how many times it landed in region 1, region 2, region 3, region 4, and somewhere else in the room. And you could actually give a conjecture for that specific person based upon their previous success with doing so. But in general, there's no way to make a claim about this particular one, right? Yeah. Okay, last example for today. So real quick one, it's COVID data. All right, so recall as of, we already did one COVID problem, this is recalling back to that. So recall as of August 1st, 2020, the total number of positive cases of COVID-19 in the state of Oklahoma stood at 37,731. The population on July 1st, the closest I could get to that date, was 3,956,971. On August 1st, what was the probability of interacting with someone who had tested positive, right, past tense, had tested positive for COVID-19? So what would we do to find that probability? Yeah, it would be a fraction, right? All of our probabilities, so probability of somebody who's tested positive, would be the number of people who've tested positive divided by what? The number that's total, the number in our sample space. So the number that we had that tested positive was 37,731, and 3,956,971 was our total population at that point, or pretty close. So grab your calculator. We're going to write down 4 decimals of accuracy. I think you'll see why when you look at it. It seems like a reasonable number. So What is the probability associated with this? Right, 0.0095. So if you think about your previous test, we talked about place values. What is the place value of the 5? It's the 10,000th place. So what this is actually saying is 95 in 10,000. I'm just making a connection to a previous section, not because you need to write this down for the answer, but that's the connection. It's 95 in 10,000. So if you were in a room with 10,000 people, which would be crazy because you shouldn't be in a room with that many people anyway, right? Obviously not. Then roughly 95 of them in that room would have tested positive in the past. Not necessarily at that moment, but in the past at some point. Okay, one more question along with these. Also, on August 1st, it had been reported that there had been 549 deaths and 30,282 people who had recovered from COVID-19. On August 1st, what is the probability of interacting with someone who is currently infected with COVID-19? I know it's like 0 because they're all in their houses, but that's not the point. I'm just looking at some numbers here with you, okay? So just bear with me for that part of this discussion. So there were 37,731 who had tested positive, 30,282 have recovered, and 549 have died. So what would I have to do with those numbers to find how many people currently have it? Yeah, perfect. We would be subtracting. So we would want to have the number of people that are currently infected divided by our number of people total. And you're exactly right. So this would be my 37,731 minus the 30,282 for the recovered folk and the 549 who had passed. And I would be dividing it by my 3,956,971. What do I get on the top? Yep, 6,900 over the same 3 million number. And we'll go again with 4 decimals. What do I have? Wait, 0017. Again, that's 17 in or out of 10,000 because I'm in the 10,000th place. Or you could say this is approximately 2 in 1,000 if you rounded right to the 3 decimals place anyway. So if you had 1,000 people, it'd be 2 in 3,000. 2 in 1,000. To give you some perspective on numbers. So Jenna got her wish. So here's what we're going to do. Well, let me just stop the recording first.